$20 today for anything.
No?
No.
Okay.
Because everyone here today is physically here today.
Nice. Okay.
Thanks.
Navigate the settings. I'm trying to disable it.
No.
I'm trying to disable it so that every 30 minutes it doesn't stop the recording.
This is my first time looking at this, so we're equally
Yeah, it's not a
experts. Okay.
Uh,
Is there a little D-pad somewhere? Oh, this. I bet you this is it. I bet you use.
Zoom.
Yeah, but I bet you. Oh no, you don't use that at all.
My camera has like a joystick.
Yeah. Well, there's some buttons over here. What do these do?
Nothing.
Oh, that opens up the menu. Oh. What if we? Oh, I somehow got here. I'm sure it's on the touchscreen. Look, it's a touchscreen.
It's a hard touch screen.
It's,
Okay.
it's one of the old touch screens with the little infrared laser beam.
Resistive touch screens.
Okay, I think this is live, like on the internet right now. Let's find out.
Hey YouTube.
Hi YouTube.
Hi YouTube.
Hi YouTube.
We're about to scare the audience away.
They can be a little bit scared of us. Yep, we're live. Do we have audio?
Oh my god, the default setting is not to have that 30-minute thing, and someone else changed it.
Okay, yeah, this is live. We have one person watching, and that's me, so we are good.
I can get my friend Dean to equate the number. When you have a second, can you get up on stage so I can position the camera when there's someone up?
Yeah, I can pretend like I'm up here giving a talk. Hello, and welcome to Embracing Open Source, Pioneering Sustainable Solutions for a Thriving Future. My name is Hong from FOSS Asia. All right, great.
I got equal view of the backpack and the stage.
Oh, nice. Yeah, I should probably take that off. I picked this up this morning at Fred Meyer for $10.
$10?
Yeah. I was looking for like a nice backpack, but they didn't have a single one. They had children's backpacks with like so it was either this or dinosaurs.
That's actually pretty good for $10.
Yeah, I think so too.
Yeah, that's a good deal. I've been wanting an LTP backpack, but they're like.
Please do not forget. Please don't forget to start this one this time. Okay. Oops. We are at the Tripping Hazard Conference. This chair doesn't need to be on stage. What's up?
Oh, I'm just remembering how to use this. Unlock it.
Yep. Well, down is unlock, I think.
Okay.
Look at the back. The back is where the sigils are.
Okay.
And then you hold down the middle button to turn it on.
Okay.
And it takes a minute, but it does in fact turn on.
I don't understand the purpose of the lock.
It's so that you can start the recording and lock it and then put it in your pocket and not worry.
Okay, that's actually smart.
Okay, this is good. Let's clean up the stage a little bit. This has to go back out there. That's the room bag. This is
That's my bag.
That's your bag. Okay, I'm not going to put shit in there.
I can
Cool. We are all set up in here, and you know what? Just for my own sanity, let's try this. Let's try unplugging Hong's laptop, unplugging in Romeo's laptop, and why did this go to a lock screen? Why did the streaming laptop go to a lock screen? Mousy. Okay, that works. Now my wallpaper, the default wallpaper for Xubuntu 2310, is on the stream for the public internet. This is going to work great. All we had to do, all day yesterday, all of our problems, we just didn't know to look for a USB port that worked.
What were the problems yesterday if that involved a USB port? Was that an
Some of these USB ports on this computer, the reason
that's
that
why you
my
can use
laptop,
that
my laptop from home was running the stream yesterday is because we tried and it didn't work. So we went to one that we knew worked. And we found out that the reason it didn't work is just because port stinky. All right. Okay. These are some good stickers.
Plus, Asia people are telling me that I should go to this conference in Vietnam.
Yo, I would go to a conference in Vietnam for sure.
I would too, but I don't know if my parents are going to let me do that. I'm going to text my mom right now and say, hey, can I go to Vietnam in April by myself for a conference?
I think you could pull it off.
They let me go to Vermont by myself for a conference, but that's like at least still in the country.
No, ask to go to Vermont again and be like, oh, that was a typo. If they raise us, think about it. You're good.
Say yes, and then I'm like, oh, it's a typo, it's Vietnam.
Alright.
Did you have the lights on the entire time?
Huh?
Did you have the lights on the entire time for this room?
I think so, until when we're moving it.
Okay, I think people want it dark so that they can
They're gonna
actually
fall
read this.
asleep.
Oh, I see. Is that the idea?
Like, look, can you read that?
I can read this. Yeah. But I think other slides were less good.
Okay, well, it'll be in the refrigerator. My personal philosophy is like, you turn off lights. But you can overrule me on that if you want to.
Or at least
The lady in the back laptop was messing around. There's very limited settings for lights.
okay.
One of the ones where the house lights are off gives us a spotlight right on the screen. Which is not what we want. So you can page through those if you want, but I'm personally happy with this.
Okay. I guess that this is the best.
Well, I don't know if it's the best. It's the one that Romeo put first, and so like, you know, you can say how many for Romeo and change it. to push the record button?
No, I didn't do that.
Okay.
Is OBS? Oh, what's the password?
User 1 space password.
Oh.
Okay.
Oh, it already is recording. Okay.
No, it's streaming. It needs to also be recorded.
Oh, okay.
Yep.
And then I'm gonna turn off auto lock.
Yeah, if you could figure out how to do that.
It's K to E, so that might be hard.
I'm gonna have to go get Mousy.
No, I got it.
Okay. I'll,
Oh yeah, here it is.
oh, you found it?
It's probably under here. Yeah. Remove dim screen.
Well, it didn't dim the screen. It locked the, like, environment. I'll find Mousy.
Okay.
And get him to give me information on this. I'm gonna go find the secret.
I figured it out.
Okay.
Let me turn the mic on for this. Not yet. I'm turning the mic.
Yeah, that's going. What's wrong?
Microphone's rolling.
I just-
This is rolling.
Good morning, everyone. Thank you for being here very early in the morning. My name is Hong Dan. I'm going to do the presentation this morning. This is my first time here at this conference, and I love it. Everyone is very friendly. A lot of people came to our stand yesterday. Thank you very much for showing your interest and support to what we do at Foxator. Before I start talking about sustainability, I will explain a little bit my connection with open source and what we actually do at Foxator. So you can see on the map at the very bottom, this is where I came from, a small city in the Mekong Delta south of Vietnam. How I get to into the open source community. Back in my university time, I think that around 2006, there was a conference that organized in Hanoi called Forthbridge. This is a conference hosted by the European Union, trying to bring open source projects from Europe to connect with the local company in Vietnam. It was the first time I got to learn about open source. I was a translator at that time. So I get a little bit of interest into the idea of sharing and collaboration, do something that benefits everyone. And then later on, when I moved on to my university, there was an occasion that there was some problem with my operating system, and a friend of mine at university installed Ubuntu into my machine. That was the first time I got to use Linux. So I still remember I was impressed that it was very easy to make a file into PDF at that time. At the moment, if you want to export like in like Microsoft Office or something, you need to have an external service, but it was very easy to do it in Ubuntu. And I like the fact that when you want to download something, it's also very fast with the software manager. So since that day, I started to use Linux and got engaged into open source. I went regularly to the Linux user group in my university, and not the software that inspired me, but the people I met in the community. I remember I was sitting down with a developer for 3 hours who tried to explain to me how to do like some simple stuff on Python. And throughout the year, I met a lot of people who are so fascinated about what they are doing. They can sleep like for hours talking to you about DBN, about Inkscape, and they seem very proud of what they are doing voluntarily for many years. So I got really inspired, and at the same time, I realized a lot of opportunities that open source can bring, like for example, like free access to resources, to knowledge, and also the connection with people around the world. Later on, I met my partner, who's also a long-term contributor to open source. We started an organization in Vietnam called Force Asia. So the mission of this organization is to introduce open technologies. I will call it to improve people's lives in the region by sharing knowledge, sharing technology, and building a sustainable force ecosystem. Over the years, we have grown quite large and also have a name, make a name in Asia, in the region. We have contributors from all over the place, you can see, and from with the community, we developed a bunch of open source software. Some we are using ourselves and also being adopted by organizations around the world. This is a few things that we developed. It's a combination of software and hardware. You can find everything here on GitHub. Open source. So from the start, I always believe in the benefits of open source, the idea of sharing, collaboration, as you mentioned. But open source isn't limited to software. What you see here is a feature that's showing relevant open movements based on the open source principles. We have open content, open data, open research, open health, open standards, open hardware, open government. Not sure if anyone has any example of open government around the world. So there is something like Taiwanese started some years ago with Gov 2.0, but this is the concept of open government. So these principles, so the next thing I want to talk about is how open source principles align with sustainability. So first let's look at transparency. So open source promotes transparency by making source code development processes openly accessible, and in comparison to the sustainability efforts, transparency is very important for monitoring and accountability. The next principle is collaboration. Open source encourages collaboration, while sustainability requires collective action. In the open source community, people share knowledge, work together across disciplines and borders. Open source enables us to leverage the collective wisdom of the local community and to build scalable solutions that can address the environmental, social, and economic issues that we are facing today. Another principle that I want to mention in the course of open source is to encourage reuse of existing solutions. For example, as you can see these days, a lot of people around the world develop similar solutions to tackle the same problem. And this is a duplication of efforts. So with open source, we can reduce duplication of efforts in compared to sustainability. This means the valuable resources are not wasted on reinventing the wheel. And instead, we can build projects based on the existing one, lead to more efficient and effective outcomes. The next principle I want to highlight here, which is inclusiveness. Open source is inclusive, allowing everyone to participate regardless of their background, and this inclusivity extends to sustainability by ensuring that a wide range of stakeholders can be involved in finding solutions. So, based on a few principles that we see here, I think that we can agree open source has the potential to revolutionize the way we approach sustainability. So moving on, I want to share some inspiring examples that already show the impact of open source on sustainability efforts. The first example is the open source in environmental monitoring and data analysis. We can look into the very basis of data collection. Software like R or Python combined with open data sets allows researchers and policymakers to analyze and visualize environmental data and enables evidence-based decision making. Open source hardware in form of data collection. So we have the pocket science app that we've seen in our desk, developed by the Foundation community. This is the open source hardware that provides a platform for citizen scientists to collect environmental data and conduct research. Talking about data, so without open data, it's not possible to verify assessment. Therefore, any initiative that focuses on open data is very important, and I want to bring up one example here from the Singaporean government. In 2011, so they released a repository of data collected by 70 public agencies, making these data freely accessible by the citizens and developers. Creating a useful solution. They even offer like APIs to real-time public data, which is still available today. And this has changed a lot in the ecosystem. Like if you're looking at the last COVID pandemic, right? Singapore government together with their citizens developed an open source application for to tackle the health issue at that time. Moving on to open source in climate change. I have two examples here. One is the climate change .ai. This is an open community of people from academia and industry working together to provide multiple educational resources around tackling climate change through machine learning and AI. Another initiative is OS Climate by the Linux Foundation. So they build analytical tools and data commons platform that help to inform climate-related decision-making and investment. Open source in renewable energy. So in the field of renewable energy, the project like open source ecology, this project has created open hardware design for solar panels, for wind turbines and other clean energy systems. And And this design can be freely accessed, modified, and shared around the world, enable communities to build their own renewable energy at an affordable price. Next is open source in smart city and open planning. Yes, so this is a very, how do you say, tradition, classic example of OpenStreetMap. So we know OpenStreetMap is the way to navigate ourselves in life, right? But OpenStreetMap also provides detailed and up-to-date geospatial data that enable better urban planning and resource application. Another project that I want to mention here is the Things Network, builds open and community-driven IoT networks, allowing cities to collect real-time data on air quality, traffic patterns, energy consumption, and it helps us to develop more sustainable urban environments. Open source in robotics. Open source is actually gaining a lot of traction these days in the world. Software like ROS or Gazebo are widely adopted in the industry. Below here I have one example of the robotic middleware for healthcare. This is an open source system built on ROS2. And it was actually deployed at Changi General Hospital in Singapore, and this is one of the biggest and most prominent hospitals in the region. So they use this open source platform integrated into their building infrastructure, like using it indoors or elevators. The next thing is open source in transportation. There's also gaining momentum in the recent year. There are two projects I want to mention here. Open source autonomous vehicle platform, AutoWare, is an open source software stack for self-driving vehicles that be on the roads. And it includes functions to drive autonomous vehicles from localization to object detection. On the top, you see Everest is a project from our partner. So this is an open source electric vehicle charging infrastructure. It's fully open source, and it also under the Linux, the Foundation Energy. I believe that just a week ago, I don't know if you saw it on the news, that the US government also announced that they want to adopt this software to make sure that different providers and manufacturers here in the US follow one single framework for EV charging. And they were promoting this Everest software. There's, of course, more examples, not only limited to those specific sectors. You can find a lot more on two initiatives that I shared here. The first initiative is the Digital Public Goods Alliance by the UN. It actually facilitates the discovery and deployment of digital public goods. And another initiative is the Open Sustainable Technology Project, provides an index of open source projects related to the UN Sustainable Development Goals. So these examples that we just saw now, they have confirmed the impact of open source on sustainability. It somewhat gives us a positive picture for the future. However, these are not enough. We need more examples like this, and we need everyone to participate in solving the world's problems. So what can we as individuals can do to participate in the movement? So starting from the very simple, to support and promote open source projects. I always believe better by sharing. So if you are here today, you are interested in the topic, and you see any project that you like, you can start to check them out, make a small contribution, even try it out, adopt them, or share this project with your friends, with your family, and the people around you. The next thing that you can do is to connect and collaborate with the open source community. So there, you see in the hall there are a number of open source communities and projects presented here. They would be happy if you stop by and talk to them and see how you can contribute. And of course, check out the project of HR. Yes, and the next thing is if you develop open source project yourself or any hardware project, you can open source is share with the world and inform your colleagues or convince your companies and others to do the same. Only by working together we can make the world a better place. So I hope that with what we see as the open source, the impact on sustainability, we can all join into the movement. I also want to take this opportunity to invite you to connect with us and to join our next summit in Hanoi next year in April. So I forgot to mention earlier, beside the software and hardware that we developed across Asia, we also run our annual events. We have the Across Asia Summit as our signature event. We have satellite events in various locations. In Thailand, Singapore, Bangkok, we also have our own tech summit. In Germany, we regularly deliver workshop and presentation at university to engage with the students and to get students to contribute to various open source projects. We run our own coding program as well. So if you are interested in what we do, check out the website called So I also want to promote a little bit about the system we use to run our events. We've been organizing events for the past 15 years. To have an event similar like this, like organize the content, getting people together, is always a lot of effort. And a few years ago, we started this platform that helped us to organize our own events, and I must say that it has released a lot of stress and workload for myself and the team, because everything automated deploys. So if you want to change something on the schedule or you want to add a new speaker, it instantly changes. So it really makes my life easier. And this project is also used by the Wikimedia Foundation to run their own annual Wikimedia event. As we mentioned earlier, we use Unity. So if you're looking for a solution to run your event, why not check out Event Day? And finally, thank you very much for your attention. If you want to get in touch with me, you can find my email there. I will be around until the end of the day in the hall at the Across Asia Center. Thank you.
Thank you, Hong. All right. And let's see. Thank you, everyone, for being here. Welcome to SeaGL Day 2. While we get our next keynote speaker set up, figured I'd come on, repeat a couple of announcements. So, step over here.
Should I be using my own computer?
Yes. Sorry. So, a couple of reminders and announcements. All SeaGL spaces are required, or all people staying in SeaGL spaces are required to abide by the Code of Conduct. And if you're in person, we have a health and safety policy. Most importantly, maybe not most importantly, but most relevant to people is that if you're in the speaking rooms and are not the speaker, you are required to wear a mask. We have masks available. If you're in the exhibiting area, masks are encouraged but not required. Aside from that, I want to thank our sponsors for making this possible. We have Schedules Direct as a gold sponsor. They've been with us for all 11 years. We also have Google as an idea sponsor, helping with inclusion, diversity, equity, and access. And Intel is a bronze regional sponsor. We could not make this event without our fiscal sponsors. We also have a bunch of media sponsors and other sponsors who I'd like to thank, such as Foss Asia for exhibiting with us this weekend. Thank you. Aside from that, I wanted to remind people that this is an all-volunteer run event, so we're accepting volunteers for next year. If you go to SeaGL.org/volunteer, that will lead you to a form that can help you get in touch with us. We also do a volunteer dim sum, so if you're interested in hearing more, tomorrow at 11 we will be doing that, and you can come and talk to me or any of the other volunteers for more information on that. Aside from that, we also have a form at SeaGL.org/feedback, and we'd love for your feedback, not only about the in-person event, but also this is our first hybrid event where we're trying in-person and remote. So whether Matrix is a platform that's working, whether Jitsi has been working, other things like that, all of these technologies become better with more volunteers, but we've put together what we hope is an excellent experience for you so far.
I don't know, man. I got a lot more tabs to close. I just figured I was going to be projecting from like a projection computer. All right, yeah. We're going to call this good.
There's a mic up here I need to turn.
Okay. Call this good enough, I think.
All right. Well, with that, I will present our next keynote speaker. This is Kaylee Champion. Thank you, Kaylee.
All right. My extremely messy desktop. Now, just a slide, maybe. Do we have slide? Yeah.
Do I click?
Yeah, you could get it.
Here, one moment.
Oh, that's my other screen. Gotcha.
Yeah, that's good.
Okay, yeah. We just need to flip them on your side.
Okay.
Sorry.
No, it's okay. I'll make it work. So I just kind of...
Yeah, that's the way. Other? Yeah, there we go.
Love it. Okay. Thank you all for your patience. Oh, see, that was not really the good move. This is how the sausage gets made.
Okay. All right.
Groovy. All right. So, yes. Now we're really rocking and rolling. I'm going to touch my clicker. Oh, look at that. Okay. So, yes, I am Kaylee Champion. I do research on free and open source software, how people work together to build amazing things. And I'm a member of the Community Data Science Collective, which is a multi-university research alliance. My talk today, Simple Dreams and Complicated Nightmares, Innovation, Trust, and Risk in Floss. I have a plan for this talk, really for realsies. So it's a little bit like the plan for every keynote ever, or maybe just kind of like the hero's journey. It makes me feel better to have a plan. I hope it makes you feel better. Here's that plan. All right, so we're going to start out with the problem space a little bit, talking about innovation, trust, and risk. Then I'll dig into some of the evidence that I've put together about that problem before turning attention toward response and exploring kind of that solution space with you. All right. So my 15-year-old spends a lot of time on Reddit, and one of their favorite places to post is r software gore. Have you seen this? It's like all the bad things that can ever happen online, and they sort of screenshot it. So this example is from National Weather Service alert. It's an emergency, shelter in place, but there's a whole lot of junk going on. Here's another great example from r software gore. You can see on Wednesday there that it's going to be negative 80 degrees, so good luck, as the Redditors say. Or, here's another example from r software gore. You can see that the price of water here is quite, lucrative or quite expensive, depending on how many bottles of water you want. And it's very funny. Everywhere we go, my kid is looking for signs of freaked out technology. They can send to the subreddit, find something hilarious, get some internet fame. Great. But where they see something funny, I see something else. For one thing, I see constant evidence of the role of software in everyday life. And there's a reason it's called gore. Some of it's quite scary. So I do cybersecurity research. Besides seeing the humor, I also see risk because it's evidence of software gone bad in the wild. And it's not just kind of glitchy phone apps or crashed kiosks that I worry about. It's things more like this. So this is a screenshot of the Equifax website, clearly hacked and not for the first time. So besides making us kind of laugh, there's a serious issue on display here because as everyone in this room I'm sure knows super well, software is everywhere and sometimes we forget about it until it fails and then someone laughs at us on Reddit, but those of us who have to fix it are probably not laughing quite so hard. So we rely not only on physical infrastructure to move through the world safely, we also rely on digital infrastructure. And much of our digital infrastructure, the most important parts really, are made from free software. Our movement built the internet, the web, the cloud, all this great stuff on a disarmingly simple basis. Let people do what they want. Organize work in their own way. Share freely, be transparent, combine their work, and insist on the same from others in return. And that's always the sticking point, it seems like, that in return part. But it sounds like paradise, right? But it's not some hippie commune here on the West Coast for us. It's just how we get work done. This huge potential for human creativity and innovation unlocked because people are freed up to follow their own passions and interests. All this, all from people just doing what they want to do. So that's the innovation part of my 3-concept title, Innovation, Trust, and Risk, that unlocks capacity to generate amazing work. I'll talk more about trust and risk as we get a little deeper into this. Oh good, my glasses are falling apart. All right. This is my representation of trust. That coffee cup balanced on the edge of the desk doesn't, it makes me a little anxious just even to look at the photo, much less imagine it in my own home. All right. Here we go. Cool. So think of just the tremendous advantage of it. People just doing what they want to do. Think about the innovation we've unlocked. People just doing what they want to do. And then think of the horror of it. People doing just what they want to do. Uh-oh. So, because in this paradise of choosing what to do, there's grunt work, although having friends to help us out can help. And some of the work we need to do might not seem all that appealing, but it helps if you have friends. The demand for our time and attention can be overwhelming. I don't know how many of you feel like Taylor Swift when you log into GitHub, but sometimes there's a lot of requests, and sometimes people really push on your time. And there's always some shiny, fresh, new thing that might draw our attention away from the thing we know we really need to do. The people who got there first in our projects might not be all that welcoming to newcomers or to people who don't look or speak the way they do. And the voice of the user, how our products are being used, how our projects are changing things out there, it's not always clear. We might not have any idea how many users we have. We might not know what they're doing. Attempts to get a good measurement might make people concerned about privacy and security. So this blessing and curse of freedom has been driving my work and that of many of my research colleagues lately. And we talk about a mismatch, a misalignment of what people want to do versus what users want to use. That form of risk where we're taking the sort of the organizational and the social and kind of smashing it into the technical, that's the focus for this talk. And if we were talking about a purely kind of market level driven model of like software development, there's a very simple economic mechanism with supply and demand to align it, that's price. But the price for the amazing software goods we produce in PLOS is free. And that's often the way we like it. And choosing what we do, that freedom, is what's unlocked so much creativity, so much joy, innovation, and I think it's worth defending. We might have an expectation that the truly important stuff, the stuff that's everywhere, it's going to be secure and great quality with lots of those expert eyeballs keeping us safe. And really, we can't all read all lines of all code. You've got to trust somebody or something in this life. Although, please don't trust random people on the internet. They will not only give you nice, non-exploiting text inputs. They really won't. And if you trust them, you'll be lucky if you only end up on our software gore. If you're not lucky, then the CDE database has some room for you. At least with open source code, though, independent review is possible. And we might expect, too, that the folks building these packages, they know their stuff's important. If there's a problem, the right people will hear about it and take care of things. Our digital infrastructure relies on a huge amount of trust in good, smart people doing what needs to be done, expertise, willing cooperation. And the good news is mostly it works, but it doesn't always. Two security issues illustrate this problem, especially around the misalignment of great secure software and user needs. Heartbleed. This is like the slide that launched 1,000 research projects. Vulnerability in OpenSSL, present for years, deployed all over the place, out-of-date architecture, maintained by just a few people. This is a screen grab of the Heartbleed test being run on yahoo.com that NPR ran as part of their story about Heartbleed. So Heartbleed happened because OpenSSL was nowhere near the quality and security we would hope for, given how important it was. Implementing all its own memory management, reinventing a lot of wheels, missing a few issues in the process. And after the debacle of Heartbleed, there's this huge influx of donated time and effort put OpenSSL back to where it should have been all along. Log4Shell, and a vulnerability in Log4j, also present for years, also deployed all over the place, small team, plus, it's a logging library, maybe it's not like a hotbed of innovation. Work there might be a bit thankless because it's just the standard thing that folks import. And a bug that was devastating in part because so many end users had no idea if or how they were using it. It had disappeared into infrastructure. And with no feedback loop to communicate to all these important users using a thing that imports a thing that imports a thing and so on, this dependency chaining is part of what can be really powerful. We use each other's stuff, thank goodness. And oh dear, our mutual dependence is both a virtue and a risk. Huge amounts of trust in those good, smart people doing what needs to be done. Heartbleed and Log4Shell are bad enough in terms of how things can break down when we have misaligned security and importance. But there are vulnerabilities getting disclosed all the time. We have what sounds like a simple dream, and these are complicated nightmares. Building evidence about innovation, trust, and risk is how we hold on to that dream and slay those nightmares. But there are other signs of long-term trouble. So to try to develop some measures about that, I did some research in Debian. And, talk about good, smart people. Debian folks are really some of the very best. I made some use of the fact that Debian puts all of its historical data out for sort of public consumption, and they're very consistent about tracking bugs and measuring usage. But how do folks in Debian know what needs to be done? To try to understand the consequences of this misalignment, how well these efforts are kind of matching up to what's important, I took this perspective of like the most highly used stuff, the most important stuff should be the most high quality stuff. And the stuff that people aren't using, it could be maybe lower quality. We want to line up the importance of things and the quality of those things. So if we take that perspective, we take that kind of schema to things, now we can lay software packages out and see how much they deviate from that expectation. So what I found, in fact, is thousands of packages in Debian that were pretty low quality despite being widely deployed. And this is not a Debian problem because Debian developers are awesome. This is an us problem. This is a problem for all distributions where the work that folks are doing just isn't that well matched to what users are using. And what I have on the screen here, this graph on the left, this is a heat map that shows kind of down in the bottom right corner. That's the bad zone. That's stuff that's very highly used and it's really low quality. In this kind of color smear slide here, or part of the slide here, these are ones where I could tell that they're pretty much lined up with importance versus quality. And here's where they're very high quality, maybe not in use. And here's things, all these packages, thousands of packages represented here, which are low quality but widely deployed. Okay. So my bet is this is a problem for all distributions where we're just not matching things up. And there's so much work out there to be done, but distributions are only one part of the ecosystem. Upstream developers are crucial too. And how we do a better job of making sure those good, smart people in FLOSS are doing what needs to be done without wrecking the joy of doing what we want it's a real question. And one way I think we do this is by gathering data instead of making assumptions. And when I published my paper about Debian packages, folks in tech wondered if it was mostly a matter of old packages. Kayla, they said, oh, this is the old stuff, right? Old languages, EC, old packages, oh, that old terrible thing somebody wrote a long time ago. Or maybe the horror of all horrors, old packages written in old languages. Okay. And IT managers and folks, they said, oh, you know what? This is a problem with redundancy. This is an issue with too much relying on a single point of failure. So I'm like, okay, these are good theories. Let's test them. So on this slide, what I have for you, these are violin plots. And what that means is we take all of the data and we arrange it as a histogram, kind of sorted by these traits. So across the bottom, we have language. And I used that same kind of schema that I showed you with all the lines to arrange the packages according to their language. And the higher things go up here, the higher risk they're at. And these are sort of roughly sorted by the age of the language. And what we see actually, for example, on the left here with Lisp does pretty darn well in terms of matching up importance and quality. C, which folks sort of suspected, it does struggle a little bit with a lot of variability. You can see how super high risk up here, but also very well maintained and clustered most of this data next to that 0 point. So pretty close actually to alignment, but there's some risk. So we can kind of work our way across here and kind of test some of our assumptions. C++, Shell, maybe not doing all that much better than C, so don't strut around too much, C++ folks. Perl and Python performing a little bit better, Java also doing a little bit better than C, but not kind of blowing it out of the water. So what you might expect if this theory about old languages is correct is you should have all the risky stuff up here, and then as you work through time with these younger languages, everything should be done here. Clearly that's not what we see. But we talked about the age of the package, so what do we got here? We've got on this slide all these little black dots, those are packages, and this blue line is like a moving average as it moves through here. So what we see is that as the packages get older, risk goes up, but then it kind of flattens out through here. It's not like a straight line going from down here to way up here. So what this tells us is that older packages are at a higher risk, but the risk kind of flattens out, and it's not kind of a universal. Okay. So I'm going to try to step through this pretty quickly too. This is about like redundancy of support. So what we see here is that the number of maintainers, we have risk at the top and low risk, high risk at the top and low risk at the bottom. And the number of maintainers, as you increase the number of maintainers, here again, the optimum number of maintainers for a Debian package is 1. Having multiple maintainers seems to perform pretty well until about here, where we start to sort of tick up in terms of the risk. The same can be said for uploaders. So these are people who are just contributing packages, not putting their names down as the person who's in charge of it, kind of in a broad sense, but just pitching in with a package. And here again, lower numbers of uploaders do reasonably well. By the time you get up into the high 20s, we're starting to get into higher risk scenarios. But you also see just a really wide variability here. All right, so what this tells us overall is that age is important, but it's not the whole story. And we don't want to overvalue that maintenance by committee because individuals can do really well. We're kind of pushing back on assumptions that older is worse or we need kind of maintenance by committee. But, common sense tells us solo work is not sustainable forever. And that's where I think perhaps what we need is just this robust community where folks are ready to step in, but not trying to, develop everything by committee so that no one feels that pride of ownership and accomplishment. We want to support people feeling committed and responsible. It's that trust in good people again. Okay, so this is sort of far short of a solution to the misalignment I talked about, and this is a lot of my own work, but there's a number of other sources of evidence I want to bring to the table here. So this slide for me represents complexity because there's just a whole lot going on. And my observations on this comes from a paper that was published in 2015. The black line is about NetApp, and then we have MySQL and Apache. And when we think about complexity, one of the dimensions of that might be configuration. So this is showing unused configuration in these packages. And what you see is that it's worse than 80/20 in a lot of ways, right? That would put us at about here. So many configuration parameters going unused in these major packages. Think about the effort that goes into maintaining and testing kind of regressions in the additions that you've made to the code base when you're carrying around all these configurations that people don't even use. All right. What they found in this paper is that configuration parameters were increasing and that it was a big area of support effort, but that many configuration options are rarely used or not used at all. And we need to know how software is being used because we don't want to break things that people depend on. Maybe once something's in there, we're afraid to take it out. But thinking a little bit more closely before we add new features that kind of proliferate this configuration space would probably help us out. But if we don't serve people's needs, we won't have the big audience that maybe we're hoping for, although this looks a little bit overwhelming. Some level of audience, though, is where Floss has real power. Often we want those users because it's where our new challenges and puzzles will come from. This is one of the key ways that our work actually makes the world better. But, there's a lot of them, and maybe not a lot of us. How do we hear from end users without overwhelming ourselves? How do we keep that freedom to create and share without screwing people over when they trust us? So one emerging practice around that is asking community members to really step up and serve as moderators, to triage those issues, enforce code of conduct, and the paper that I'm sort of citing here on this particular topic, they found that there's not that much software support for moderation in our bug tracking systems, and so thinking about how we can enhance our own tools to serve us better would probably be a big opportunity. Another kind of area to think about here is with respect to the software supply chain. So I don't know how many of you have heard of the software bill of materials movement. This is the idea of articulating in a standard format what you're using out there. And there's a lot of tools that can help us to generate these SBOMs. And the finding of this one that I think is really exciting is that those organizations that had taken the time to implement SBOMs found that they were able to respond to the Log4Shell vulnerability in just hours, while those that did not have this sort of documentation of their dependencies took weeks because they didn't know where they were using Log4j. All right. So the next kind of piece of insight that I want to share comes from this notion of longevity, and I chose the banyan tree to represent longevity because the way that it lives, it's almost immortal. It has, instead of a trunk and branches model, instead the branches grow their own roots and it retrunks itself overall. And I feel like that the ability to live forever by retrunking, rerooting ourselves has a lot of lessons. All right, so my insight, this is like my checkbox, hooray, I got it, graph, and it looks super simple, but let me tell you why it's exciting. This is from some studies that I did in Wikipedia, and I want to make a fast case to you that studies done in Wikipedia can tell us a lot about software, because just as with Linux and other areas of open source, this is an area where people contribute where they want, they organize themselves, they're not bound by kind of top-down structures, and we have the same kinds of problems in Wikipedia that we see in open source in terms of the things that sometimes people want most to use are not always the highest quality. So neglected articles of very high interest topics and so on. And so the finding here, this line that goes up, these are those kind of high risk areas in Wikipedia. Those are the high interest, low quality articles. And across the bottom, what we have, people getting more and more experience. The lesson from this is as people get more experience, they're shifting their contributions in Wikipedia toward underproduced articles, those articles that other people want to read. And I feel like that holds a lot of interesting lessons for us in open source, because we can think about retaining our contributors because we believe that over time their interests will be more for the good of the project and perhaps less about their very immediate, oh my gosh, this is crashing my computer, my server is waking me up at night, I need to fix it. And over time, if we retain our contributors, perhaps their goals will shift toward the good of the project. So retention, I think, is a key part of how we continue to build a sustainable ecosystem in FLOSS. But, and this is also kind of a funny looking slide, what we see in Wikipedia, and I'm sure we see in open source as well, is different trajectories for all different people. So again, we have the kind of the risky stuff up here and the low risk down below. And some people over time just kind of move into those niches, and some people over time are moving toward the good of the cause. And I think that we're likely to see that in open source as well. So as people gain more experience, their interests definitely shift. The good news for us is that means we can influence each other's choices in positive ways. And if we're able to shift that toward the good of the cause, then that helps FLOSS become more sustainable, more aligned, and less likely to show up in software war. Okay. Oh, and one other, I guess, caveat is that although retention is awesome, keeping people around is a great idea, there's also a risk of oligarchy forming. So that sort of sense of like, okay, here we are, we're the people who have been here the longest, and we're not maybe going to let any folks come in, is also a risk as we retain folks in FLOSS. All right, so here's the story that I've tried to tell you so far. We're going to bring it all together. FLOSS is core digital infrastructure. Older packages are not doomed. Our freedom is worth protecting. Ignorance leads to wasted effort. We face huge demand. That's Taylor over here. Community members can skyrocket. Usage can be unclear, but tracking our supply chain can help. Important software is getting neglected out there, and longevity helps, but can backfire. So where I'm going next with this, I'm trying to tackle this problem because I'm still short on a solution, is to try to understand how this neglect emerges over time, identify these problems before failure. And one angle that I'm thinking about is trying to target communication flows, signals of trust as they're exchanged, and signals of need. All right. So to sum up, I want to invite you to take action in 3 regards. Know and be known by your upstream. How are you tracking the dependencies of what you depend on? Are you helping your favorite project to make an SBOM if they don't have one? Are you auditing your own software bill of materials? Are you opting into those surveys and data collections? Know and be known by your downstream. How do you communicate what you're planning? How do you hear what others want and rely on? Do your users know what they're using, and how do you reach them if you need to? And finally, how do you choose what to work on? Can you put yourself out there just a little bit, spare some effort for work that's truly for the good of the cause rather than your own direct needs? And think about what projects keep you up at night. Where are we tolerating a gory and miserable decline in quality? Innovation, the freedom we have and must defend to create and share. Trust is inevitable for making progress, but needs to be based on more evidence and better signals of what's safe to use. And risk, part of being human and making software is having bugs. Software gets old too and needs patching and refactoring and often retiring. But knowing where neglect is creeping in to projects that we rely on, knowing what we're using in the first place, is how we confront and manage that risk. The paradise of open source is still here, mostly, but we've got to protect it by caring for it and each other. Smart, creative people doing what needs to be done, that's you. Thank you all so much for your attention. Let's talk today. I'll be here all day. I'm very eager to connect with all of you. Thanks.
Thank you very much, Kaylee. All right, and thank you, everyone. I'm excited for day 2 of SeaGL. Once again, if you are attending in person, please wear masks when you are inside the presentation rooms. And we do have plenty of those desks. Go take a look at the exhibitors. I just realized, and I forgot this yesterday, and I really want to mention today. I don't have a list of names, but this conference would not happen without all the volunteers who have put in countless hours. So thank you all. Have a great day.
How are you measuring active quality?
Sure. So I knew I left something out of my presentation. Yeah. So the metric that I use is mean time to resolution. So it looks like they're going to see what it actually does. So mean time to resolution on the
That was excellent. You were talking. Going from over
most of the kids
yeah, so that's where the garage right here.
at San Diego where my brother lives. And worked my way out here. Everything I complained about for 40 years. It's what you need. You need rain, clean air. Summer and winter. And back in the day, you have to have a generator. And I want to talk to this guy. I am a pastor.
an AV check next, I think.
Yep. All right.
And I joined
I feel bad. I didn't realize this was a Linux laptop only affair here. So
Oh, it isn't. Absolutely is not. We're
I
not-
know. I think I'm the only one who brought my Mac.
I would be. I'm surprised by that. Honestly, we really
It's fine.
we've gone through a lot of
and
we've gone through a lot of making sure that we don't mess with yeah, okay, there you go, yeah, we've gone through a lot of making sure not to be
and currently a member
Yeah.
of the club
operating system
that I quit in
bigots.
about 1984.
It's a tricky thing in the free software world because 10 years ago you would go to any Linux conference and that would be a thing. Oh look, that's the person not using a Mac. It's like
I kind of been
that shouldn't be what we're about.
Oh, okay.
Yeah, it's fine. And
Anyway, you gave me
Yeah.
understanding.
I like that, the pinstripe. Very nice.
Thanks. They don't seem to make this one
No,
anymore.
I haven't seen that one in a long time.
Yeah, and
Yeah.
and the store's like closed now, except for by appointment.
I know. I haven't gone to their new store in Interlake. I keep meaning, or Interbay. I keep meaning to go, but making an appointment on it.
Yeah, who has time?
Right. Yeah, I actually make my own now, so that's
Oh, wow.
yeah. I'm eventually going to open source my pattern.
81
Nice.
going.
Yeah, I've been trying to find alternatives, but all the ones I've tried are just disappointing in comparison, like to the quality. Because like these have lasted me like 10 years.
So same. Yeah, no, I killed one in survival finally, but like
Yeah, why not?
And, and nobody, no male in my family to 70.
Oh, wow.
I will. This seems to be fine, so
That's
I
great.
Yeah.
Thanks for coming and
I'm the
checking.
oldest of three brothers. And those
don't have any audio or anything complicated, so.
This guy's been around forever.
Yeah.
And,
Yeah, you've seen me grow, shrink, grow.
Yeah, if I had have got your email, I got it yesterday.
Yeah, no, I know. I'm so bad. I'm so bad.
And I've been,
And I love the hair.
now that I've
I'm
been resettled here, I got an apartment here, and I may never go back to the town. This is one of the best places in the world. And I'm out in Snohomish. Lots of money. And you know, that kept the air free. So when I moved to Virginia with my wife, she had trouble breathing. So this is.
Yeah, I didn't have to eat food or have coffee, so I need to.
You're under instructions.
Hey Jay, you have everything you need right now?
Yeah, I think so. There wasn't anything else in the blue box, right? Yeah.
Scene collection. Wonderful. It works perfectly.
Okay, good.
See, this is what hearing aids do.
Sorry.
Make sure everything's set up.
No worries.
Oh, wait, there's no mic.
Just make sure I have everything out of my pockets, or I'll play with it while I talk.
The battery out on this. Okay, it's good. Just give me like a 30-second warning before we start.
Yep.
So I can turn on this OBS and then that mic.
Yeah.
To pop it.
Just making sure I have all of the noisy things closed.
You ready?
We still have a few seconds, but yeah, I'm ready.
Okay, this is rolling. OBS is rolling.
This mic's rolling. So I'll give people just a few more seconds since it's not quite 10:30. Might as well get started. So this talk, in case there was some confusion with the schedule, I don't know if there was today, but there certainly was yesterday, is going as fast as possible in Rust, an in-depth look at optimizing the quadratic sieve. And I will be your host for this. My name is Christopher Swenson. I currently am a software engineer at HashiCorp and previously at many places. I'm really passionate about programming languages, cryptography, math, sorting. I have a book, and you can find me on Mastodon or around here. I will also try to check in on the Matrix channel after this for this talk to see if there are any questions. But I probably won't have time for questions in this talk. And so what are we going to talk about today? So the title sort of outlined it. We're going to talk about the quadratic sieve. And I'll explain exactly what that is here in a minute. And then we're going to talk about Rust, and then optimizing Rust specifically for the quadratic sieve. So very quickly, the goal, quadratic sieve is a factoring algorithm for factoring large numbers. And if that isn't super familiar to you, factoring is the process of taking a number, typically a very large number in our case, and trying to find the prime factors that divide it. It's a really important problem for a lot of cryptography. So a lot of protocols like TLS and SSL use RSA, which uses the fact that factoring is hard as a basis of security. And when I say large, in most cryptographic protocols today, typically we're looking at a number n that is thousands of bits large. And I will talk a lot in bits, just because that's how I always think about these things. If you think in decimal digits, this is something like hundreds to thousands of digits large. But in general, I will talk in bits in this talk. And the quadratic sieve in particular is an algorithm that works really well for numbers that are roughly in the range of 100 to 300 bits.
It is not the fastest algorithm that's out there, but it is actually quite simple to talk about and to implement, at least a basic implementation. And luckily, it only really requires very basic algebra to get through. So while this sounds like a really heavy math thing, it's actually like nothing that someone who doesn't have took a high school algebra class should totally be comfortable with this. I hope. I also feel that implementing the quadratic sieve is a really great kata or meditation that's good for your programming soul. It teaches you a lot. It's also a lot of fun, and it is also completely worthless in terms of its actual practicality itself. Almost worthless. So the best kind of programming example, but it's also very detailed. And so a sort of motivating program for this talk was a program written about 15 to 20 years ago called MSIV. And MSIV is a program written by, I hope I'm pronouncing his name right, Jason Papadopoulos, almost entirely by him. It's still updated very rarely today, but basically the development stopped about 15 years ago. It contains a couple of factoring algorithm implementations, including the quadratic sieve, which is what we're concerned about today. And it's really, honestly, just a complete work of art as far as code goes. It's really beautifully written, extremely high-performance C, and also it has a little bit of assembly as well. And it's meant very much for x86, which was the dominant architecture at the time, and x86-64. And I thought a few months ago, or earlier this year, what happens if I took this C program and just re-implemented it in Rust? I was this was the gold standard C implementation of this algorithm 20 years ago, and the gold standard of languages today is Rust, right? At least for low-level things. So that's very opinionated. I'm not even sure if I fully agree with that opinion, but it seemed like a fun exercise. And so I thought, I'll re-implement it today in Rust, try to use the same sorts of tricks so I can get a mostly apples-to-apples comparison. And it's single thread, single core, no GPU or anything too fancy like that, just a really kind of straightforward implementation. And then we'll optimize it and see where we get. How hard could it be? This could only take this program took years to write. Obviously, it only take me a week to get it rewritten right now. Spoiler alert, I'm still working on it. It really took a few weeks to get the core of it done, and there's a lot of room. Every single win you get from this point on just gets further and further away. So it gets harder and harder as you go. But it took many weeks to even get a good start. All right, so let's talk about, let's get into the sort of factoring landscape for this. So if you remember from high school algebra, there was every now and then you might have seen a difference of squares come up, a squared minus b squared. And when I saw this back then and today, I immediately think, oh, well, that's a plus b times a minus b. It was this identity that was sort of burned into us way back then. Hopefully, it makes an echo in your mind that, oh yeah, I remember if I have a plus b and a times a minus b and I multiply them together, it comes out to a squared minus b squared. And you might think, oh, well, maybe I could sort of use that for factoring if I think about it. If I can maybe express a number as a pair, as a difference of two squares like that, and I know what those a and b's are, maybe I could factor them. And that's exactly what Fermat's method is. It's a classical method. And it basically says, let's look around. If we have a number n is always the number we're going to be factoring. And if we start looking around square root of n, and we kind of look for squares around there. So if we look for numbers that are perfect squares, and we check to see for every one of them if a squared minus n is also a perfect square. And if it is, then we can rewrite that a little, and we get n equals a squared minus b squared. And because of number theory reasons, that has a 50-50 chance of factoring that number. So if you know A, you know B, you can check A plus B and A minus B and see if they have any factors in common with n using greatest common divisor. The greatest common divisor is super easy, so that's not a particularly challenging part. The hard part is finding those squares that satisfy this. It turns out as the number gets very large, this time grows exponentially in trying to find this. It's not a very efficient algorithm. But it is the core idea of what we're going to go for. So the quadratic sieve is a couple of refinements on that idea, but it really is still a squared minus b squared. Like that is the ultimate goal. We want to find a squared minus b squared that will let us find a plus b and a minus b. So instead of looking for a single number, a squared, where a squared minus n is a perfect square, that's a big lift, I would say. Like, it's a pretty difficult thing to try to find numbers that have that like perfect property. But what we can do is we can look at a bunch of a's, a squared, a0 squared, a1 squared, whatever, and then if we find not necessarily that they're perfect squares, but that when they're multiplied together, we get a perfect square. So specifically when a squared minus n times a squared minus n, like all of them multiplied together are a perfect square. Even that's a little tricky, like just doing that and hoping to randomly find them, like that might be like a kind of daunting task. But one way we can do this is by looking at a squared minus n's that have a bunch of common factors, preferably like a bunch of like small prime factors, because they'll likely have those in common. The smaller the factor, the more likely it is that they will have them in common. By the way, some terminology that I might use, I'll try to keep the terminology to a minimum, but whenever we have a number like a squared minus n consists only of small factors, we call that a smooth number. And also, whenever we find such a pair of like an a such that a squared minus n is smooth, meaning, again, only small factors, we call that a relation. So when we want to combine those relations to make a nice perfect square. So this just gives us a little bit of math that we can rewrite things, and we get, again, the difference of two squares for our number. I'm going to give a concrete example, because that was like a lot of symbols, and hopefully that was the hardest part of this whole talk, was just like looking at those symbols. But I think seeing an example will like crystallize this, hopefully. So let's try to factor the number 493. Like, not a big number, but it should kind of illustrate what we're going for. And again, we want to kind of start around the square root, because hopefully if we look around the square root, we can find a bunch of numbers such that x squared minus n or a squared minus n are small, and small numbers are probably more likely to be smooth. So if we look around 23, where x or a are 23, we find two relations. We find one at 26. So 26 squared minus 493, you can check it on your calculator if you like, but it's basically 3 times 61. So those are the two prime factors. And if we keep looking around, we'll find another relation, 35 squared minus 493. Again, remember, 493 is the number we're trying to factor. We can see that 35 squared minus 493 is 2 squared times 3 times 61. And you might even immediately kind of see, like, if we multiply those right-hand sides together, we would get a perfect square, which is exactly what we're looking for. So, yeah, we can construct a perfect square there. Our perfect square difference is 26 squared times 35 squared for A, and 2 squared times 3 squared times 61 squared, and that's going to equal 493 times something. We don't care about the something, that'll kind of go away, but that's what we're going for. And just to show that that does, in fact, factor the number, we can use that to get a plus b and a minus b, and then we can check the greatest common divisor of those two numbers with 493 gives us our two prime factors. So we lucked out. It's every time we run this, we get a 50-50 shot. This one, obviously, a hand-picked example, but this illustrates, this is exactly the algorithm we're doing. That's really all it is. It's a bunch of looking for these squares minus n that factor into the small numbers, and then trying to find a combination of them that, when multiplied together, will give us a square. So in order to make it a quadratic sieve, though, we need a few more pieces. We're going to need more than two relations in general. This is obviously a very small example, and the larger the number that we want to factor gets, the more relations we're going to need, and the more prime factors we're also going to have to keep track of. We need to, if you looked here, or especially here, we care about really the prime factors, and we really care that when we multiply them all together, that it's a square, which means the exponents all are even. So 0, 2, 4, and so forth. And to do that, we need we'll generally keep track of those in a matrix. We can keep track of all of the prime factors in a matrix, with one column for the 2s and one column for the 3s and one column for the 5s and so forth. And honestly, we only really need to keep track of whether or not it's even or not. So 0 is even, of course, so anything has a 0 number of factors that it doesn't contain, and then everything else we want to keep track of, is it a 1 or 2 or 3 or 4 or so forth. And we can do that in a binary matrix, so it doesn't take up a whole lot of space, hopefully. We typically limit our relations to, on the right-hand side of that, the B values to only be small primes. It just makes everything a lot easier for us. And then the really neat trick that makes this a quadratic sieve, the quadratic, by the way, is the fact that we're looking at squares. And then the sieve part is the fact that we can use a sieve to speed up this search greatly. So we can use it to enumerate those values efficiently. So let's talk about what a sieve is, because you probably are familiar with the word, but that may be a little bit further back in like high school math. But again, it's very relatively simple arithmetic. So let's talk about the sieve of Eratosthenes. If you line up all the numbers, all the integers, I should say, and you want to basically use the sieve of Eratosthenes to find all the primes. It's just a simple algorithm for finding prime numbers. And the way it works is you always ignore 0 and 1. They're not primes. We don't care about them. The first prime is 2. And we just sort of know that. It's also the first number that appears. And once you find a prime in the sieve of Eratosthenes, the algorithm is take a prime and you cross off all multiples of 2 in it. And so we cross all of those off. We know those can't be prime, right? Primes have no factors other than themselves and 1. So we cross off all the multiples. And then the next uncrossed off number on our list is also prime. So we take that and we repeat the process. We cross off all the multiples of 3, and then the next unmarked number is going to be a prime, 5, and then we cross off all the multiples of 5. And we just keep doing that until we get to about the square root of the top number we're looking at, which in this case is around 7. And then we know that everything left is prime, just because we would have hit it with one of those marks otherwise. So pretty basic sieve to find prime numbers, like nothing but like just simple marking down numbers on a nice linear array. Now, what can we do to make this sort of a sieve? So we're not looking for primes though. We know what the primes are, hopefully. We're looking for smooth numbers. So numbers not necessarily that are prime, but we want the ones where we made a lot of marks, really is what it is. So instead of keeping track of like the marks that we made like that by just Xing it off, let's actually keep track of every single prime factor as we go. So every time we marked off a 2, we add it to like that entry. Every time we marked off a 3, we add it to that entry, and so forth. We actually will have to go through and do all the primes that we found now instead of stopping at the square root. That way we can kind of keep track of like what numbers have a lot of small prime factors. We also are completely ignoring squares and cubes and things in this. Like we don't care about 2 squared or 3 squared or 3 cubed, even though they're very important. It's just a detail that gets complicated, and it's not worth worrying about. And also, I'm already kind of starting to think about this as a programmer and a computer scientist, and I'm like, I don't want to really keep track of like a bunch of factors in like linear memory. Like so far, it was like a nice linear problem. Like you just allocate a block of RAM and start like marking stuff off. But once I start like, having to keep track of arbitrary numbers of stuff in there, it gets complicated. So let's not do that. Let's instead just add in the logarithm. So we'll keep track of one number for every entry, which is the logarithm of the numbers that we're at. The logarithm base 2, because we're programmers here. We don't care about E and all that kind of stuff. So we keep track of the logarithm base 2 of all of the factors that hit that. So every time you do updates for 2, you add 1 to that entry. Every time you do the updates for 3, you add, oops, I think I missed 1 or 2 there. Or no, that's 2.6, not 2.6. So you add 1.6 for every 3 and so forth. So basically by looking at this grid, you can now start to see if I look at larger numbers, as in larger sums of logarithms, those are likely to have a lot of small factors. And again, since we're not doing squares or cubes, we can't exactly tell what all factors hit it, so we still need to like maybe pick it apart and ironically factor it to figure out what the small prime factors are. But this gives us a clue as to which entries are likely to be full of small prime factors. this is the key insight that makes the quadratic sieve work. Now, that's great and all, but this is just for plain old prime numbers. This has nothing to do with the number we were factoring. So now how do we kind of take this idea and make it about the number that we're factoring? And the way we do that is we can sort of adjust it so that we can look for numbers where x squared minus n is divisible by those primes. There's kind of a neat trick. And to sort of show you that trick, let's look at some examples here. So I just enumerated in like Python or something all of the numbers x for which x squared minus n, and here is 493, the number we were talking about earlier. I want to know all the values such that x squared minus n is divisible by 2 or 3 or 5 or 7 and so forth. So I can kind of enumerate those, but it's kind of maybe hard to see any patterns there necessarily. You might also notice that 5 and 7 are missing. It turns out, if you look at it a little bit, there is absolutely no way for the number x squared minus 493 to ever be divisible by 5 or 7. This has to do with math properties, but we're not going to get into those. And we also are just going to completely ignore 2 because 2 is annoying and not particularly interesting. But if we look at, say, 3, we'll notice a pattern here. If we take every other entry that is divisible by 3, x squared minus n is divisible by 3, we get 23, 26, and so forth for every multiple of 3, starting at 23. And also the number after that has the same pattern, 25, and then every third number after that is divisible by 3. And the same thing is true for 11. We get 25, 36, 47. Every multiple of 11 after that is divisible by 11. So this is the exact sort of pattern that the sieve at Eratosthenes did, but now we can do it for enumerating numbers x squared minus n that are divisible by those primes. And by the way, just like math trivia for you, if the reason why these numbers are like in pairs like this is because if you have a number x squared minus 493 that is divisible by 3, you can always have the same number minus x is also going to be divisible in the same way. Minus x squared is x squared, right? And so that's why you get that sort of reflection there. So all those have to do with the root of that equation and then the negative root. That's why they always come in pairs. But if that doesn't make any sense to you, don't worry about it. Just know we have an algorithm, we can find where those numbers start, and then we can just tick off every single one that's divisible by that. And then the quadratic sieve is do that, and then look for numbers that got a bunch of marks, and see if those give us smooth numbers, and then use those smooth numbers to build a square. And then now we have the 2 squares we can try to factor. That's all the quadratic sieve is. Everything else is just dressing. So let's write some Rust. So this is what we probably all came here for. I love the math. Not everyone loves the math. But I think it's still kind of cool to see, because it's, I think a lot of people probably assume the quadratic sieve is much more complicated than it really is, because it has a really intimidating name too. So let's write it. So we have our area of RAM. So we just allocate a big old block of RAM for our logarithms. Basically exactly what I said to do. This, by the way, is sort of the naive algorithm. We'll work on optimizing this as we go. We go from every single p and the primes there. I'm not going to get super deep into the rustiness of this. I mostly just kind of want to focus on getting the code out there, and then we can talk about optimization specifically in Rust. Rust is a fascinating language that makes this kind of some things easy and some things hard. But yeah, just do exactly what we said before. The first few lines are just, we need to, for every single prime, we need to kind of grab the root and calculate that starting index. You don't have to worry too much about exactly how that is, but it's basically just doing a little math to figure out what the starting point is for our sieve. And then the while loop is the sieve itself, where we add every single logarithm to every entry that's divisible by it. I mean, that's the core loop right there. Or you could also do it as a for, but I did a lot of benchmarking for this, and the while is faster. So some of those zero cost abstractions in Rust turns out cost a little bit sometimes. So sometimes it's just faster to do a little while loop and increment it yourself than try to calculate the exact start and end, which you could also do, but it involves division and stuff, and it isn't free, it turns out. Okay, so that was the sieve. That Congratulations, that's the sieve that will do the sieving part of the quadratic sieve. Now we have to do all the work to actually like try to use that to factor a number. And the first thing we need to do is look inside that sieve for the really nice smooth numbers, or the potentially smooth numbers, let's say. So typically this is called scanning. So we need to look through that array so that, that for loop there is kind of what I'm mostly, I guess I can point with my mouse. We need to look through the array and look for every single entry where it is greater than some cutoff. We won't worry too much about what that cutoff value is because it turns out it's very important, but we can just do a crappy job for now and it's fine. So we basically just pick some number out of a hat, look for all the large numbers, and then that's it. We'll kind of grab those. And then now we need to actually check to see if those values are actually smooth. And this is where the ironic part comes in, where we actually have to do a bunch of factoring of small things, hopefully, or smooth things in our algorithm in order to factor a bigger number. So factoring, it's all factoring all the way down. So we look at every smooth point. We basically we do some calculation. I just pulled whatever bigint library was popular. I think it's num_bigint, that crate. And I use that to do my calculations to calculate, okay, we have that a value, now we want the a squared minus n, or x squared minus n. So that first line just calculates that. Then we need to factor it. I won't go into details on how we do that, but we could just do something simple like try every prime up to a certain bound. Like, that's fine for now. And then we multiply all those together and make sure that we aren't missing anything, like we found all the factors. And if we did, and all the factors were, in our factor base, I didn't use that term before, but basically our factor base is all the small primes up to a certain bound. If all the factors are known and small, then we have a relation. And so we can construct that and put it into like a vector of relations. Now we build the matrix. So we talked a little bit about that matrix before, so now I want to actually show it because it's kind of neat. So we take all those smooth numbers we found and we build a matrix out of it. So looking at our example from before where we had those two relations from the number 493, we can write down a relation for every single entry. So our 26 squared minus 493, we want to keep track that 26 was the number it comes from, and these are our prime factors, and these are the factorizations. So we didn't have a 2, so that's a 0. We did have 1, 3, and 161, so that is a 1 and a 1 for our exponents. This, by the way, is because of the fact that logarithms and exponents are sort of linked in this way, so we can add logarithms. It's the same as exponents or numbers being multiplied. I'm not going to show the code for this because it's really just tedious bookkeeping, like it's just a bunch of just shoving things in a vector and stuff. So we're going to skip the code on that because we only have so much time. And by the way, we actually don't really care about the left-hand side and the top side when we want to actually solve this matrix. That's just bookkeeping information. As long as we keep track of it somewhere, it's fine. We'll need it later. And also, we only care about the evenness and the odd, like we said before, so we can sort of reduce this down to a binary matrix. And the goal is to find a sum of rows that equal to 0. If you think about that, if you sum the rows and they're equal to 0, that means that all of the entries are 0, which means all of the exponents are even, which means that it's a perfect square, right? So the whole goal, find a combination of rows that when added together is all zeros. There's a name for that algorithm. It's called a left kernel, and we don't care about the details on that too much right now. And I super don't care for this initial implementation. So the initial implementation that I'm writing, I just wrote some code to just write out this matrix in ASCII format and then call some math software to solve it for me, to solve the left kernel. Because the details don't super matter at this point. So I use Sage for this. Okay, so now we've gotten a bunch of, now the linear algebra has come back and we have that list of rows, and now we can use that to construct our a squared and b squared, and then we can use that to find a and b, and then use those to find a plus b, a minus b, and try to factor. So I will show that, even though it's mostly bookkeeping, just to show it's not magic. We literally just go through our result vector here is I think go with my mouse. The result vector, we just check to see is this is this part of our solution or not? Is this row turned on or off? And if it's turned on, we add it to basically a running total to keep track of A, and then also have some bookkeeping so that we can keep track of B, and then just do that there. Don't worry about understanding this necessarily, other than maybe noticing that Rust is maybe a little verbose whenever we're working with big numbers, because we have to do a lot of conversions back and forth. We have to do a lot of cloning and stuff, because Rust is a real, like, pedant about memory management, and so it wants to be very explicit that you're not, like, freeing the memory or using it in some way. So we have to do, like, I'd say a lot of extra hand-holding of Rust to tell it how to do this, as opposed to, say, a language like Python, which really doesn't care at all, and you could just write this and it would be pretty clean. And then we literally take exactly what we did and try to calculate the GCDs, just like we did before. Luckily, those are built into our big integer library, so we don't have to do anything special for those. And then we will get a factor in G1 or G2, or if we get one, we get one or the other as well. So those numbers are either 1, they're n, or they're a factor of n. So with 50% probability, it's one of the first two. 50% of its probability is it's a factor of n. Okay, that was the basic algorithm. So deep breath. Now we're going to start the optimization phase. So that was the really naive implementation, like we're doing the basic stuff. We're throwing it into Sage and letting Sage like solve a little matrix and see what comes out. And now, whenever I start optimizing, like you could benchmark. There's a lot of things you could do. Like benchmarking is a really great tool. But the first thing I want to do is collect timing information. And so the easiest way I think about collecting timing information in a program like this is to throw it in like a global map or a dictionary or something, and just use that and just like add in every time we go through. And the one thing that Rust hates more in the world than anything is globals, mutable globals. It really, really hates those. It's going to fight you tooth and nail every time. So we're not going to do that. And then so the next thing is like, well, what does this look like? Is this like a hash map of strings to like number of seconds? That's what I want to do. Rust doesn't like that either. Can't do that. Have to do references, because strings aren't really a type, but references to strings are. But then Rust has like a lot of questions about like, okay, where does that string come from exactly, you say? So like, okay, like fine, we'll just like divine them at compile time, all the different labels that we could use. And now Rust knows where they live, and that's what a static string is. But what if we do want to compute them at runtime, Rust? I hear you saying, and which is exactly what I do need to do. And then it gets even more complicated, and we have to fight Rust. And at some point, I just give up, and I make a struct that has a ref cell in it, which means I can mutably change it without taking mutable references. And I throw that all in an RC and just call it a day, and I just don't care. Like, the performance of this timers is not important enough for me to like really optimize this. So, and this gets my code compiling and gets Rust out of my hair so that I can get back to optimizing the quadratic sieve and not trying to figure out how to have like global timers, right? So it is what it is. By the way, all these tweets I'm showing are from ReductRS, which is this great Rust parody account. Mostly Rust. Programming in general, though. Okay, now we have timing. So let's start running our program and seeing how it does. So I just did a very basic like run through with an 80-bit number. So it's the product of two 40-bit primes, multiply them together, and then I run the program to see if it can factor them, and it came up with this. The parameters, by the way, are the SID size is 1,000,000, and the factor base is all primes up to 2,000. And those just, again, kind of come out of a hat. It's sort of an art more than a science at this point, although there are scientific bounds you can put on them. Picking the right ones is extremely important and also very difficult to describe. So I picked them out of a hat for now. I also later wrote an optimization program that runs over my program and then tries to find optimal parameters. So this comes up with a matrix that's like 200 by 200 or so, and like the numbers are really interesting. Notice that all of our time is basically spent in this left kernel here. Like 99.6% of our time is calling out to Sage to compute that like matrix thing, and that seems weird. So let's take a look at that, and we take a look at that, and Sage takes like a second to even start, and then it's got to like interpret your code as Python code, compile it to bytecode, run it. There's like steps involved, and It's not necessarily that Sage is slow, it's just that there's just a bunch of stuff going on. That was a poor choice. Let's see if we can figure out how to do that a little bit better. I just kind of went and looked at Wikipedia's entry for left kernel, because that's what we're trying to compute, and just did the Wikipedia-ist implementation ever. Like just the most basic implementation you could possibly do. I again looked at whatever popular crate there was for doing linear algebra and grabbed in algebra's D matrix. That stands for dense matrix, by the way. And I said, we just want to have byte entries, because that's a small, so let me make them. We only carry about 1 bit, but we can only do bytes. So I just made a matrix of basically byte entries that are 0 or 1. And then I ran a Wikipedia implementation I implemented it based on Wikipedia's description. And now that's much better. Now the left kernel takes 0 time, basically. There's only so much precision I can show. And this is a slightly different run, so the numbers are going to be different a little bit every time because I randomize it. You don't want to optimize for one number in particular because that's too dangerous. And there's a lot of variance in these. But this kind of lets us compare like our improvements, hopefully. And now, okay, we can kind of see like we made some improvements, and now it runs in like 0.01 seconds, which is so low that it's almost hard to measure. So let's do a bigger number to make the numbers bumpier, and then we can kind of see what's really going on. So let's bump it up to a 120-bit number and see if we can find some weak points that we can start optimizing. And this is my typical optimization strategy: is get it working, and then see how much it hurts where, and then try to optimize that, and then just iterate and iterate. And then when you do that about 20 times, you basically get the program that I ended up with. Similar parameters are just kind of scaled up. We get a slightly bigger matrix. It's still relatively cheap to compute that left kernel, so we're not worried about that. We are noticing the 2 big steps are the line sieve itself. By the way, I forgot to define that. Whenever we're sitting out it's a very, very large block of RAM like that, we typically call that a line sieve because you are like sitting down a line. So that's why it's called line sieve here. So that takes a fair chunk of time. The smoothness checking also takes most of the time now. So the smoothness checking was that like trial division of all of the potential points. The cost is it's determined by a few things, and it is always going to be an expensive part of our calculations for smoothness checking. And it's really determined by 2 things. There's a tension between that cutoff that we calculated. So if we set that cutoff too low, we're going to look at too many points, right? So we'll be looking at a bunch of things that aren't necessarily smooth, trying to factor them and failing. If we set it too high, we won't get enough, and then we'll have to look harder, bigger sieve, and do more primes and stuff. So that's just going to make everything take longer. So we get this sort of tension between, getting a good cutoff value and then also trying to get a good smoothness checking algorithm by factoring things small. So we did our initial calculation, and I just did a number that's like 3/5 the size of that number we're trying to factor. And that's okay, initially, but the bigger the numbers get, the less precise that is. And so a better algorithm that I kind of came up with was recalculating that number every so often based on the actual value of x squared minus n. X squared minus n being the thing we're going to try to factor. Just every 64K of entries in our sieve, I just recalculate that and use that as a cutoff. So this way, as those numbers grow, which they naturally will start doing, we kind of retune our algorithm as we go. So hopefully this will it does a little bit better. Not a ton better, but now it's not the dominant cost, at least. So we can make improvements to that, and we'll come back to when smoothness checking is dominant again. So the next thing that's dominant in this, sorry for jumping around, is the line sieve is now the majority of our time. So let's take a look at that line sieve that we did. Before we did, you might remember that simple little while loop. This is maybe a slightly different version. I kind of mixed and matched a little bit from various pieces of my code. But the key was really this while loop here. We do some index calculation, and then we just loop over it. And we do that for every single prime and every single root of that prime. So there's always 2 of the roots, like I said, that give you those starting points. And the fact that I just said that there's always two roots, and we're doing one and then the other, we could just do them both at the same time, right? That kind of makes some sense. The roots always come in pairs for math reasons, and so we can actually just combine them, like we said. So we just do a quick little sort. There are ways to do it necessarily without sorting the roots like that to try to find those initial indexes, and then we can do a double sieve, basically, I'd say. So you want to sieve both of them at the same time using only one index. The actual details of like the index calculation that I do there are not super important, but basically you can restructure it so this while loop here, the main while loop can sieve both values using the same index by just doing an initial offset calculation. And then you have to do a little cleanup if you want all the extras. Maybe one of your roots was a little larger, a little smaller. You don't want to like run off the end of your array because now we're in unsafe rust. Before we were doing safe rust and just plus minus equals inside that, and now you might notice that we switched over to using raw pointers. And so we have to be a little more careful about our indexes now. And why are we switching to unsafe? Well, now we're into the fun area. If you're not familiar, by the way, with godbolt.org, or the Compiler Explorer, as the tool is called, this is a wonderful tool for sort of figuring out what's going on in your code. And I apologize, this is quite difficult to read. But the gist is our old code on the left, where we had that simple while loop here, actually compiled down when optimized into a fairly straightforward loop, but don't worry if you don't know the assembly language. But the key is that up here at the top, every single time, we're checking if the index is in bounds. And then if it isn't in bounds, then we have to panic, right? So this is part of you get in safe rust. Safe rust always checks indexes in arrays. But that's silly because if you sort of look at this, the actual code here, which is a little more visible, we're only going to, from index 0 to area is the maximum size, we're doing that check ourselves anyway, right? So why are we, making it do that again just so that it can panic? And so instead we rip out the safety because we're already doing that calculation anyway. And if we do that, then we see it get a much smaller, much tighter loop now. So it saves us, you might think that extra two operations per cycle doesn't matter. It turns out it matters a little bit. And the bigger the numbers get, the more it matters. So that helped a little bit. So yeah, if you're ever in doubt of what your code is doing, I definitely recommend using Compiler Explorer. Maybe one of my big wish lists from doing talks like this is always, I wish it could be integrated into my IDE so I could just pop it out. And you can kind of get into it if you look into the LLVM debugger output, but it's way complicated and painful, and I'd rather just have a little pop-up that says this is the assembly for the code you're pointing at right now. So my wish list. So we're doing a little bit better now. Not a lot better, but a little bit better. In order to do even better, we need to talk about RAM. People may or may not be familiar with the concept of caching. But caching is basically having smaller chunks of RAM, usually in or very close to your processor, that are very fast, but at the expense of being very expensive and very small. So there's a trade-off between speed, cost, and the space it takes up. And it has to do with a whole bunch of stuff we won't get into, but there's sort of a hierarchy of RAM. Typically, modern processors have 3 levels of caching before you actually get to the real RAM in your system, the real memory. And one of the worst kept secrets in computing is the fact that memory has not gotten faster in about 40 years. So this latency number here, from a latency perspective, is the same latency you would have seen in the 1970s. And the only way we have saved ourselves was in the 90s or so, modern processors started adding layers of cache to try to make applications more performant. Late 80s, early 90s is really when it started taking off. And typically these numbers have gotten a little bit faster. The L1 cache has to stay very close to processor speed, and then they get progressively slower and bigger as they go. So these are the numbers from my Linux desktop, which is a Threadripper. It has a lot of L3 cache. Most processors have a little bit less than that now, although we're starting to learn that bigger caches help you a lot. But the typical L1 number there is really, really important for what we're going to talk about here. It's 32 kilobytes of data, 32 kilobytes of instructions. We mostly care about the data. And we might have noticed from our previous timing information, our SID size has now grown to 50 million entries. Each of those entries is a float 32. That's 4 bytes. So we have 200 megabytes of memory that our SID is taking up, and we're constantly enumerating primes all the way to the end of it. So we're loading it into RAM, loading it into cache, doing a bunch of work with it, which immediately trashes the cache, and then doing it again and cycling. And that's really inefficient. All right, we're completely destroying our cache every single time we iterate through that array. By the way, kind of interesting note, I'm running this on a Mac with an M2 processor, and one of the secret ways that Apple has made these things so fast is they have drastically increased the L1 and L2 cache sizes. And this is what makes these laptops so much snappier than most ARM processors. And also, if you look at the memory bandwidth on the right, it sort of makes kind of sense to get slower and slower, but it's not clear exactly what some of these bandwidths are, but the main memory bandwidth is absolutely monstrous on these things as well, which is just really bizarre. It made it actually running all my code on this laptop really tricky because you optimize it in a very different way once you start taking this into account. But so let's get rid of the float 32s. And let's switch it down to just a byte. So we just have a single byte for every single entry. This will save us a factor of 4 in RAM. So that seems like a pretty obvious first step. And we just, take those logarithms we were doing and just round them up. And it's a little sloppier now maybe than it was before, but that's okay. We can kind of absorb that into our smoothness checking to account for that. And now our line set time has gone down a little bit more. It's still not great because we're still looking at 50 megabytes of RAM and constantly trashing our caches. And as let's scale up again just to kind of exacerbate that, and we see that this is really the dominant cost as we're getting bigger and bigger is this SID cost here. So this line SID line will just keep getting worse and worse as this gets to be 250 megabytes or something. How am I doing on time? Terrible. Great. So a real cool innovation of MSID that is, as far as I know, is the first one to come up with this, is we're sitting over this huge area. Maybe we should try to actually concentrate our SID in the L1 or L2 portion of memory and not constantly thrash caches. So it came up with this sort of algorithm. I don't know if there's actually a name for it, but it's basically this, you split the SID into 2 parts. Look at larger primes that maybe don't even necessarily hit every single L1 block of RAM. If they're bigger, if they're wider than the L1 caches, if the prime is greater than 32 kilobytes, it's not even going to hit most blocks, right? It's going to hit every other block. And so every single time it hits, it's going to be like a cache miss, right? And so that costs a lot. So we'll split our factor base into 2 parts. The ones that are bigger, actually, it always does 3 times bigger than the L1 cache size, and then all the small ones as well. So for the bigger ones, instead of actually incrementing all those entries in memory like we want to, we'll just keep track of those in lists. So we'll just basically, it calls them for some reason hash tables. It's not technically a hash table, but basically you can just keep track of all the indexes that you would have incremented with the logarithms that you were going to add in. And then for every single L1 cache block, we just do everything we were going to do, for the entire algorithm in that L1 cache block at once, and you add back in the medium primes as you're kind of going along. So just to maybe visualize that a little bit here, our whole SID area is this big long 250 megabyte or whatever array, and we really only care right now about this L1 size. We pre-computed all of the entries for our larger primes, our medium primes, and those look like, for this hash bucket 0, maybe this is 0, this is 1. We have this index wants to get this logarithm update, this one gets this, addition, and so forth. So the first thing we do is we SID out those small primes. So we just go through every single small prime in our factor base, and we SID out everything in there. So hopefully everything is nice and fresh in the L1 cache. We have very few misses. And then we then add in all of the updates for our medium primes. So this is a really cool way of taking advantage of L1, and this makes the numbers just way, way faster. I broke down the numbers now for, instead of line sieve, into allocation, the medium calculations, the medium updates themselves, and then the small. And actually our number, if we notice here, our factor bases, our primes only go up to 38,000, which is less than 3 times the L1 cache size. So these are all, the medium primes don't even come into play here. So that doesn't matter. But now that we're doing this in this way, our number is, we were at like 30 or 40%, and now we're down to 13%. So we're getting like a factor of 3 like X improvement just from that. And we haven't changed anything. We're still computing out like the exact same array in memory. You could like take the array in memory and it'll be identical to the previous one. So we just change the order in which we do our updates. So I think that's a super cool algorithm. And now one thing you might notice is that like it's a small optimization, but like we are still allocating like a huge 250 megabyte block of RAM. And if we kind of think about this, we're doing everything for an L1 block, and then we move on to the next one. And it's like we can actually just reuse that block of RAM that we just did. Like we could just look into it really fast, scan it, and then zero it out, and then redo it. Now we don't have to allocate anything. We can actually do an entire 256 megabyte block, but only do it in one single 32 kilobyte chunk of RAM. And that's cool because we noticed that it takes like 27 milliseconds just to allocate 250 megabytes of RAM. Like, so we just get to eliminate that. And that would only get worse as the numbers get bigger because at some point we're going to run out of RAM, right? So now we basically don't need any RAM to do this algorithm, which is super cool. It doesn't save us much, it just makes that number go to 0. So now our smoothness checking is getting a bit ridiculous now. It's now like 40, almost 50% of our running time. So we need to like take a little bit of a look at that and see if we can do a little bit better. And we could again either try to adjust that scanning threshold, or we could try to just factor it better. So I did a bunch of stuff, and I'm not going to go through the Rust code for all of it. But we were using num-bigint, which is a very popular library, and it turns out it's just not very good. Like, I mean, it's fine, but like when you're talking about high performance like operations, it's just not there. The gold standard in the industry is GNP, the GNU multi-precision integer and also floating point library. I think it has MPIR or whatever. And there is a nice Rust wrapper around that called rug. And then we can also do a few things where we basically try to optimize these numbers for the small primes and whatnot. I'm not going to go into detail because I think I am running very low on time. But essentially we can try to do a better job for some of the smaller primes by optimizing some of those calculations. And that makes this way, way faster. So instead of 50%, we're now down to 2%. So that's cool. That's probably good enough to get us to the end of the talk for smoothness checking. And now we're still here with a fairly large chunk in the actual sieve itself, some in the matrix code as well. Some of the linear algebra is starting to poke its head up a little bit here again, like 20%. So let's talk a little bit about that. Even though it doesn't matter now, it will become the dominant cost as I grow the numbers bigger and bigger. And we were using, like I said, that N algebra D matrix bytes. And I think we could do better than that. So again, we're really talking about like bits that we care about, not whole bytes. So we're getting some inefficiencies there. And we might be able to really pack in and take advantage of 64-bit numbers and try to pack in bits into that, as well as we could even talk a little bit about SIMD instructions. So like vector instructions. Rust has this great portable SIMD extension that I think is being added soon, if it hasn't already landed, that allows you to make really wide types like 256 or 512-bit integers that kind of look like arrays as well. There's like a mapping, but it will use really good instructions under the hood. And so let's take a quick look at some timings. I did a factorization off screen of a 220-bit number. I built a matrix, and then I tried to implement the linear algebra for a few different kinds of matrices to see what improvement we can make. Our baseline is just using that D matrix we were using before with byte entries, and it takes like 20 seconds just to do a solve of an 11,000 by 11,000 matrix. If instead I write our own custom matrix library, a binary that uses U64s, so it just does simple bit packing. It just shoves the bits in, and this way it can do really efficient like row and column operations where you're doing a bunch of XORs, which is basically all we're doing. If we do that, we get it down to 2 seconds essentially. So massive, massive improvement by a factor of almost 8 or so. And then the next step I was thinking is like, well, what about if we extend this wider so we could try to take advantage of those SIMD instructions? Like, you know, your AVX 512s or on ARM, your Neon instructions. And the answer is actually it doesn't help at all on, at least on my Mac. This shows a weakness of the Mac processor, of the M1, M2, and M3 processors. They have a really weak vector support. They have 128-bit Neon, is what it's called, and it's just not very good, honestly. The AVX 512 and then soon to be hopefully AVX 10 for 1024-bit ones on x86 processors is much better, and I saw a much bigger improvement. But at least for my my M2 processor here, it didn't do a very good job on that. So it wasn't really worth it to try to extend this out to use these SIMD types. And I tried a bunch of different SIMD types, and it was always not great. So that was a surprising bit for me. And some of this is also because LLVM does an okay job with some of these auto vectorizations itself, especially on x86 processors. So the benefit is not necessarily perfect there. The one place I did find SIMD scanning was super beneficial was for scanning. So that we're, again, if you think about it, at one point we're looking through that whole like block of RAM and we just want to find big values. And it turns out there's some SIMD instructions that do that really well. This is what it sort of looked like before. This looks kind of awful, but essentially we just calculate our cutoff and splat it across, you know, a bunch of value, or like a wide array type, and then we have to just do a single check here, the SIMD greater than equal to check, and this checks, you know, every single entry at once, whether or not any of them are greater than it, and then if any of them is true, then we have to like go down and actually look at every single one. But hopefully, like this main loop here, where we're just doing these huge SIMD greater than or equal to's, will save us some time. And it turns out it does. That saves, again, like a factor of almost 8 or so on my laptop with its kind of bad SIMD, which is kind of cool. So it takes us down from 20% to 2%. So we're chipping away. Since I'm basically almost out of time, where did we get to? I'll try to kind of start wrapping this up. So these are the numbers from running on my laptop with the latest and best version. It contains more optimizations that I could really talk about here, some of which are in the Mac itself, and some are in, you know, more exploring SIMD and whatnot. But these are the numbers I sort of came to for factoring numbers. It's extremely good at factoring small numbers, obviously. There's a very high variance as we get larger and larger. And then we get down to about 240 bits, and then it takes like a couple minutes. So that's not so bad. We haven't talked about MSIB in a while. How does MSIB do? And this is super hard to read, and I apologize, because I found when doing my MSIB benchmarking against us that it wasn't fair. So we take advantage of our large L1 cache, 128 kilobytes or so, but MSIB has a default set from 2004 or whatever of 32 kilobytes because that's what all processors at that time had. And it didn't conceive of M2 processors having a 128 kilobyte cache. And so I kind of did a little fixes in MSIB so that it could take advantage of the L1 cache, because otherwise it's just not fair. And once I did that, the top number here is 22 seconds versus our 140. So it's still like a factor of 7 times faster. If I didn't do that optimization, by the way, it's about like twice as slow. Just from increasing that cache size, hard-coded constant in its code, it gets a 2x speed improvement. That's how important these like L1 optimizations can be. It's like the minorest difference in your code that makes a massive performance improvement. So that's all the numbers are showing. Very hard to read. So sort of like, again, we're actually a little bit better than MSIB for small sizes. But that's because I spent a lot of time parameter tuning and getting really good parameters for small sizes. And MSIB has kind of like a really sloppy parameter set. We're in a factor of, I think, 4 to 8 or so for the larger ones. There are things that we can do better, and that I will. What are some kind of quick lessons here? Do I have any time? I have like 3 minutes maybe. So Rust and LLVM are pretty good at doing this, better than I honestly thought they would be. They've come a long way in the years. Auto vectorization is really great. And it did do a lot of really fun, cool auto optimizations with some of the scanning and linear algebra. I honestly found a few maybe bugs though. Sometimes when I would try to use cool methods like fill to say 0 out an array, it did a terrible job. A factor of 2 or 4 times worse than if I just did it in a little for loop, which I found very strange. I haven't had time to dig into it, but it seems to generate bad vector code for that or something on a Mac. The modularity is nice, and honestly, Rust is a lot of fun. I like Rust. However, Rust has a brutal learning curve. The memory management is very, very difficult to get a handle on. I feel like I have to do a lot of the work for the Rust compiler to tell it where memory is going to live and how it's going to be managed, where some languages will just be we'll just throw it in the heap and figure it out later with garbage collection, which is good and bad. It's good for ease of use, but bad for performance. So, and we care about performance, so this might still be the right one here. I'll skip over that last point and jump. If you want to learn more about this, there's a really great book called Prime Numbers, The Computational Perspective. It's also basically the only book that talks about the quadratic sieve, as far as I can tell. And luckily, it's really approachable for programmers. Most of the other books that do mention it are very heavily geared towards professional mathematicians. So this one is a very pragmatic approach to most of these algorithms that involve prime numbers, including factoring. Looking at MSIV is great. Godbolt is great if you want to learn more about what your code is doing. The quadratic sieve Wikipedia entry is surprisingly good. It has a lot of references that have more information, a lot of implementations that you can look at for inspiration. And then these slides are available now on my website, swenson.io. And that is all the time I have. Yep, 1 minute left, so no questions. Come find me after.
Good talk. Thanks. I practiced it several times to try to get it under 60 minutes. So my apologies, but there was no way I could make it at 50.
This is all way but that's okay. And yesterday I just met a gentleman. He's my age, and he doesn't take any medication, just like me.
Cool.
But his name was Russ.
No, neat.
Do you know him?
No, I don't.
But I see that Rust was a...
Yeah, the Rust programming language. I don't think it has anything to do with the person, though. We do need to leave, though, so they're going to start another.
Good job, thank you.
Hey, are you the next speaker?
Yes.
Okay, cool. So we need the reservation for this room expires at 12.
Okay.
So we need to be out of here
I'm at
12.
20.
Okay, awesome. That's
As
fantastic.
of last night, 22 minutes if I'm going slow.
That's fantastic.
I do, yeah. I'll get you understood. Thank you. Can you actually, while I do that, can you give them a crash course on running the stream?
Yep. Right now? Yeah, I can.
And then just let them run the session and you can answer questions. Okay, does that make sense?
Yep.
Okay, cool.
Do the other rooms have that same mic setup? Okay.
You mean the podium?
No, the tiny mic.
They're not sketchy, if that's what you mean.
This. Do the other rooms have this?
No. Because the other rooms are actually mic'd.
Oh, okay.
So yeah, and yeah. Right.
So the rundown. We're gonna add all of the footage of the speaker talking and post-processing.
Okay.
So we have a camera pointing at the speaker. You hit record. There is a 30-minute limit on this camera, so you have to start another recording after 30 minutes. So pay attention to that. There's been a couple of times where I haven't done this for about 5 minutes. And then on OBS, On OBS right here, for non-virtual talks, you would have the scene set to be local live, and then that goes through the capture card, which has it go through to OBS and the projector. The stream should always be running.
Where'd you set local live?
It's in scene collection right here. We're live right now. They can hear us talking. And when the talk starts, hit start recording right here. And then this is only for this room, but make sure this mic is rolling too. Alright, this mic's rolling. And yeah, a little bit more you have to do if it's a StreamYard talk. That one's a little bit more complicated for a StreamYard.
Hello, friends. Hi. My name is Sira. I am the owner of Capital Hosting Solutions, and my very short presentation today is about my baby, the company Capital Hosting Solutions. 5 or 6 years ago, they told me I couldn't game on Linux, and that it just didn't work. So I said screw it and started a game hosting company on Linux. Who am I? I'm Sira. My pronouns are she, her. I'm the owner. This is also my first talk I'm ever giving, so have some dog tax. It helps make me a little less nervous, and I hope you enjoy my beautiful dog. That out of the way. Dogs are cool, but what is this really about? Yeah, it's about my hosting company. Quick, who's on the team, who's our user target, and then the real meat and potatoes, which is kind of our systems design overview and philosophy, and then how we make changes, and then also how we try to give back to open source. Quick meet the team. There's me. I'm the Chief Chaos Officer. I do a lot of our systems architecture stuff, most of our network engineering stuff. I'm also the owner. This is Judd. He lives in Australia. He's the co-owner. He does a lot of our back-end stuff as of late, and more front-end stuff in the past, and we're kind of moving around back to that. Lemma, it is our resident bytecode sorceress, Java programmer, and also one of our 2 support engineers. Vivi, she is also our other support engineer. They handle the brunt of our tickets surrounding direct game hosting problems and kind of what we like to refer to as off-the-street customers, like non-custom solution stuff. Ellie, she's kind of my co-systems automation and stability person. She's actually back there hiding. Yeah, another good friend of mine. And then one of our open source developers, Matt. He's kind of our contractor, receiver of contracting budget. He's the primary maintainer for the game hosting panel we use, Pterodactyl. And we try to pay him what we can when we can. He's a super cool dude. Wish he was here too, but didn't work out. Our target customer, do they play games with an online server component? Yes? No? Cool. Awesome. They do? We love them. And that's all the easy stuff. Now the fun stuff, the mile-high overview, if you will. How we do things and why we do them. We try to use hardware vendors who don't really get in our way. We've had experiences with a couple who have and have made running off-the-shelf Linux OS a complete pain. Weird firmware stuff that we have to pull from them, not even things that are in Linux non-free. But vendors who have, Supermicro, Quanta, and Dell especially. ASRock Rack's been pretty good as of late, and then MSI, then AMD all day long. Love them. They just work. As far as our philosophy goes for design, use Floss software as much as possible where we can and how we can, and then document everything. Travel knowledge sucks. We use Notion for primary documentation. We started that about 8 months ago, and it's been all right so far. It's very, very good in Markdown, very, very good as a Kanban board. Sadly, we can't use Floss everywhere. We're not good enough developers. We don't have enough time to dedicate to running or building software that's completely open source to use for ourselves all the time. We all have day jobs. So we had to make a couple hard decisions. We had to use WHMCS over Blesta. WHMCS, if you don't know, is the de facto billing portal if you're running a web store, unless you're paying for Shopify. And it's closed source. All of their code and binaries they're obfuscated, and their documentation is a little out of date as well. Blesta, which we tried to use in the past. Open source, everything is kind of just there. It works. The team who supports it, the maintainers of it are amazing people, and I love working with them. The other hard decision we had to choose was Plesk. We had to choose it over AA Panel. AA Panel's kind of a really cut down version of cPanel, a little bit simpler, a little bit more up-to-date interface. And yeah, but it didn't suit all of our needs. It crashed often. It wasn't documented well, and when it did crash, it didn't log correctly either, which was a fun one. So we ended up moving to Plesk, more closed source software, much sad face. And then a couple easier decisions were made. Pterodactyl panel, we paid a maintainer of Pterodactyl to make changes for us, to help us with changes we're making, and kind of add features if he would come up with something. And then Proxmox, greatest hypervisor out there. VMware, not so much. Yeah. As far as our game node hardware goes, pretty much off-the-shelf components. Throw them in a box, rack them, network them. Ryzen Pro CPUs are the only not true off-the-shelf component. We have to eBay those, and they're generally scrapped from enterprise gear. High-speed RAM, non-ECC, actually, because Ryzen CPUs have a history with ECC memory, if you're unfamiliar. Other than that, simple boot disks, and then all of our storage is on RAID 1 arrays on higher speed SSDs, or either NVMe's or SAS SSDs. As far as software goes, Ubuntu LTS. Docker, all of our customer instances run inside Docker containers as non-privileged user. And yeah, and then we also run MariaDB server because some games require a database. And unfortunately, MariaDB is a little hard to run sharded. So we just dedicated instances per node, and then part of the migration process, if we need to bump a customer over, or all of the customers often have to do maintenance, everything moves over, creates a new table, and yeah. And then we run one of the two pieces of Pterodactyl is with the Wings daemon. It's the management the management tooling for all the Docker containers that talks to the customer-facing panel. We've got a fork of it with some changes from upstream, mainly quality of life stuff for ourselves as management, but also a couple customer features are in there as well. We jump pod agent. I think they're working on open sourcing their agent software. Don't quote me on that. That's how we handle all of our SSO, login, and then we use Dropbear SSH as our server component rather than Open SSH. It's lighter, it's faster, and is generally less picky. And then we use UFW for firewall management. And then everyone knows CertBot, everyone knows the Nginx plugin. That's mainly for ensuring we've got valid SSL certs on all of our nodes that aren't private certs, so our customers don't need to add our own root CA for talking from the game panel to their nodes. Now we get the fun stuff, the control plane hardware. Generic rack mount server. We kind of get whatever we can get our hands on. Quantas, Dells. We had HPEs at one point, some Supermicros. E5, V3, V4 Intel chips are newer, and then 2.5 SAS base. If we can get U.2 support for NVMe's, we can. If we can't, we can't, and we use riser cards. We only use one 120 gig as a boot disk because we can walk into any of our regions and yank a node. It goes offline and everything comes back up. So we're not too worried about a node just disappearing. And then 2.5 or 2 terabyte NVMe's for our high speed storage, and then 1 or 2 terabyte SATA or SAS SSDs for the rest of the 2.5 slots. And then Intel NICs. Intel has been really, really good at making sure their network interfaces just work. A couple of hardware photos. A little bit of lab porn, a little fox in there. His name is Carl. And these are what kind of our common node deployment looks like. This is actually a photo we took last week in the West End as we were gutting some nodes to replace with newer versions. As far as software goes, Proxmox, we've mentioned it. And all of our stuff runs in LXC containers, except for a couple customer VMs. And then all of our storage backing is with Ceph. We've worked with the Ceph team a little bit. We've made a couple pull requests recently for features around monitoring. We use multiple pools. Our NVMe back storage is high-speed stuff for databases or Kubernetes workers and anything that's an end-user facing application. And then everything else goes on SAS or SATA SSDs, usually Samsung's, Micron's, and HGSDs. And then again, we replace OpenSSH with Dropbear Server because it's lighter. A couple of quick screenshots from the panel, kind of showing what I think this is our Seattle. Yeah, this is SEA1's cluster. We have a lot more stuff in there that I can't talk about in the show, just from projects we sponsor. But otherwise, yeah, we've got everything bounced into LXC containers. We also have a couple virtual machines. Our web hosting customers, Plus runs better in its own VM. That's really the long and short of it. And then we've got LibreChat. We like to keep them segmented from everything. We sponsor a node for them. And then kind of our deployment philosophy. Containerize what we can, shard and initiate what we can. If it can be deployed with ISE, it should be. We haven't settled on something we prefer yet, whether it's Terraform or Chef or Puppet or Terraform and Ansible or, yeah. And then if it can be reproducible, it should be. We try to sign all of our containers and we directly reference every single version in every single dependency we use, so we have the same build every single time. Whether it's being built on my rig at home for dev or in the CI pipeline for prod. Quick shout out to the reproducible builds folks here. They're super, super awesome. They have a lot of really, really good stuff about kind of getting to the point of doing reproducible things. And then the fun stuff. How we make changes. We do it often, we do it fast. We kind of fly a little loose with it, but that's okay. We encourage change control. If we're deploying something that's not from Git, we're doing something wrong. And I don't think we have anything that isn't in Git at this point. And whenever anybody makes changes, we encourage people to put in separate branches. It allows us to do MRs, allows everybody on the team to provide input and review changes that are being made, whether it's something they understand or don't. It allows other team members to ask questions around the why. And then once we kind of get either one or two members, we shoot for 2-member approval minimum, we merge it, and then the CI pipeline takes over. Automated, we hit go, we merge the main, and it deploys. We don't need to touch it almost ever. One thing with that though, a lot of people really subscribe to the agile methodology around sprints, like, oh, you have to deploy, like you can't deploy until a sprint's complete, everybody needs to see every change, you need to do reviews. All of us, let's see, we've got 2 people located here in the Pacific Northwest, 1 in US Central, 1 in Australia East, 1 in Australia West, 1 on the East Coast, and then someone that we consult every once in a while for Ceph help is in Europe. We can't do sprint meetings. It doesn't work. So we just don't. We just all check, get notifications, and go, hey, cool, let's put our reviews in. And then talk, approve, merge, repeat. We do it this way because it works. It serves our customers best. We have a relatively small customer base, all things considered. They like it. They get new features when we get them done. We get to announce stuff sometimes. Yeah, we've tried a handful of things. We've gone around. We've settled on this. It's not professional, but let's be honest. We're a game hosting company. What do you mean professional? We care about customer-affecting changes. We don't care about how our reviews look to people looking into our org. And it works for us. And then how we give back. We try to give back to open source where we can and how we can. We pay Matt a portion of our profits that come from game hosting. He's a Pterodactyl maintainer. It's his job right now. His entire income is sponsorship and money that comes from us and a couple other hosting companies. And we sponsor a few other projects too. Free infrastructure, sometimes assistance. One of the projects we sponsor is not an all the time infrastructure sponsorship, but a when they need stuff sponsorship. And sadly, there's a lot of projects that are looking for sponsorship, but we just can't give everyone everything. It equals resource strain. Kind of the way we review who we sponsor is we've got a few questions we ask. Do they have a community conduct policy that actually is inclusive and not just exists to check a box? Is it something that our team or our customers would use? And then the really big one is, do they have other major sponsors keeping their lights on? In a lot of cases, that's for the project we sponsor, the answer to that is no. And that's because we're not really a big sponsor either. But we give where we can. And then the fun one is there fraud, waste, and abuse oversight for the way they use their sponsorships, either money coming in or resources they're given or however it may be? If yes, cool, awesome. If no, we try to avoid them. And then some projects we sponsor. We sponsor the QuiltMC project. They're a fork of Fabric, which is a modding framework for Minecraft. We sponsor LibreChat. We run currently one node for them. Of course, we sponsor the Pterodactyl project through paying Matt and also making commits and working on CD reviews where we can. And then another project we kind of sponsor in an unofficial capacity is the Tesla Scope. It's an API tracking tool for like if you own Teslas. Yeah, that's really it. Here's how you can find me on the internet. I'm currently unemployed as a day job. If you're looking for DevOpsy, cloud, syseng people, I would love to fill that hole for you. My resume is found down there. Otherwise, are there any questions? Like how we do things or why we do them? What you got?
What motivated you to start Capital Hosting?
So what motivated us to start? So about 6 years ago now, we were sitting on the floor in my living room and we went to play Minecraft together, but none of us really had any hardware to run a server on. And so we set up some gear for ourselves and we ran it like a company because we knew we were going to use it like a sandbox. And about 6 or 8 months later, the friend of Ruby who came up with that unfortunately passed away in a car accident. We all kind of looked at each other and went, okay, we got to do this for real now. Anyone else? What you got?
For your container management, what do you, like, I read Kubernetes and Docker on there somewhere, but like, do you use those for your deployment? Like, when someone asks you, I want a server, what do you do?
So the workflow for that works is customer goes, okay, I want a server that does, let's say, a Minecraft server. They go to the billing portal, they click the buttons. The billing portal then makes a post request against the game server API, creates their account with their username, triggers the password generation, and an email gets sent to the customer with the credentials. From there, the game server panel talks to the worker nodes. It's all managed with the Wings tooling from Pterodactyl, and then a Docker container gets spun up with the requisite image, startup scripts, and yeah. Anyone else? Yeah, I think that's it then. Thank you for coming to my talk. I will likely be here most of the rest of today. Find me later. Thanks, y'all.
So then when everything's done, you just have to sponsor to solve all the
Stop.
Thank you. Ooh, I almost dropped this. That would have been bad.
So the recording can stop on that one.
Yep, stop. And then I stopped recording on OBS, but you keep the stream going.
Okay.
And then...
Is there any
Where do you do that?
placeholder or anything you put in there?
It's just a black screen right now because nothing's connected to the projector.
Okay.
What
did you do
It's
again?
going to display anything. Just hit the stop recording button. Keep it streaming though. Make sure you don't click stop streaming.
Stop recording, keep streaming.
Got it. Okay.
And do other rooms have a camera too, or?
As far as I know, this is the only room I've worked. I worked this room yesterday too, but as far as I know, they should.
Okay. Okay.
This is the only room for this though.
I see.
Yeah, I wonder if they're built into the room.
I probably have. There's like a cheat sheet to deal with StreamYard, but StreamYard's a bit more complicated, so I'd probably talk to either AJ or Rumble.
Okay. Yeah, so I think they said they were going to run up there and try and make sure things are running smooth.
That was like the perfect training talk.
What's that?
That was like the perfect talk for training.
Yeah, no, that was nice. Well, thank you.
Maybe I should go down there because they're more your reading, so they might ask you. I only recently learned charisma and it's gotten shorter.
And we're sure there's nothing more, huh?
Unless somebody moved some stuff to room 1 and didn't tell me, but I feel like they should have told me because I'm the one running all the room 1 streams. So
This is you? Okay, so I don't know which. I know this is ours, but I don't know what all.
I don't know.
Else is ours, so I can just.
Don't end the stream yet.
Okay.
Because I don't know if it might break something. I'm gonna ask.
Okay.
I'll go and ask AJ.
Okay.